All right, today we're doing a deep dive into a really impressive LLM optimization. We're talking about a 24x speedup, and it all comes down to how you handle the key value cache. We're going to walk through the 4 different versions of the code step by step to see exactly how they pulled this off.
So, here's the plan. First, we'll pinpoint the real performance bottleneck when you're working with LLMs. Then, we'll follow the developer's journey through 4 major changes, starting with a dynamic approach, hitting a wall, then having a breakthrough with static memory, and finally, fusing the entire generation loop. It all leads to one key idea: coding for the compiler.
You know, the main challenge here isn't just about writing Python that works. It's about writing code that plays nice with a super demanding compiler, in this case, XLA. XLA has really strict rules about how you manage memory and structure, and if you break those rules, you pay a huge performance penalty.
And at the absolute heart of all this is the KV cache. See, when an LLM generates a response, it does it one single token at a time. The cache is what stops the model from having to recalculate everything it's already done for all the previous tokens. It's literally the engine that makes a responsive AI feel fast.
And it's so important to understand these 2 different phases. The initial prompt processing, that's usually pretty quick. But the token generation, that step-by-step process, that is what a user actually perceives as speed. If your generation is slow, the model feels slow. So this whole optimization journey is laser-focused on making that token generation phase fly.
Okay, let's get into the code. The first 2 attempts are exactly how most of us would probably approach the problem intuitively, but they fell right into a classic compiler trap.
Version 1 was the most straightforward, get-it-done code you could write. The cache was just a simple list of key and value arrays, and for every new token, you'd just concatenate the new data onto the end. Simple, right? Well, from a programmer's perspective, yes, but for the XLA compiler, this was absolute poison.
And the reason is this one concept: dynamic shapes. Because that array grew with every new token, its shape was constantly changing. XLA loves to work with a fixed computational graph. When a shape changes, it's like a brand new function to XLA. It has to stop everything, throw out its old plan, and recompile the whole operation from scratch, every single time.
And you can see the brutal performance impact right here. V1 was crawling at just 3.1 tokens per second. Version 2 tried an in-place update, which only bumped it up to 5.2. The fundamental problem was still there. Even an in-place update meant the array had to grow. So from the compiler's point of view, the shape was still dynamic.
So this led to the big architectural shift. The developer realized that tiny incremental fixes weren't going to cut it. The entire memory structure was the problem. The solution? To just completely abandon dynamic memory growth.
And this brings us to version 3, pre-allocated buffers. The idea is brilliant in its simplicity. You create one large, fixed-size cache buffer right at the start, big enough to hold the longest possible response you'd ever need. Yeah, you might waste a little memory, but what you gain in speed is astronomical.
This approach gives the compiler what it loves most: static shapes. The size of the array never changes. You just keep track of an index to know where to write the next token's data. For XLA, this is a dream come true. No more recompiling. It can build one single, highly optimized plan for the entire generation process and just execute it.
And here's the magic you get in return for using static shapes: compiler fusion. Instead of the CPU telling the GPU to do lots of tiny separate little jobs, the compiler can fuse them all into one big, efficient instruction. This slashes the communication overhead.
And the results, look at this. They are dramatic. Token generation speed in version 3 jumped from a painful 5.2 tokens per second all the way up to 35.4. That is a massive leap, and it's 100% because of the switch to a static memory architecture. That's almost a 7-fold increase, just from changing how memory was managed. Think about that. Generating 100 tokens went from taking 19 seconds down to less than 3. This right here proves that committing to a static architecture was the game-changing decision.
Okay, so the memory problem is solved. The data is now static and totally compiler-friendly, but there was one last bottleneck hanging around: the control flow, the standard Python for loop that was managing the whole iteration process.
And that leads us straight to version 4. Here, the developer took that Python loop and completely replaced it with a functional programming tool called SCAM. This was the final piece of the puzzle, moving the entire process out of the slow Python interpreter and into the compiled, optimized graph.
So what exactly is scan? Well, think of it like this. A Python for loop tells the compiler, okay, do step 1. Then, all right, now do step 2. It only sees one step at a time. A scan operation is different. It says, hey compiler, here's the blueprint for the next 100 steps. You figure out the absolute best way to run this whole block. It lets the compiler fuse the loop itself.
And bringing in scan gets us to our final, frankly, incredible performance numbers. Token generation more than doubled again, hitting 72.9 tokens per second. That brought the time for 100 tokens down to just 1.4 seconds.
This chart just tells the whole story perfectly. You see that tiny little bump from V1 to V2, then the enormous architectural leap to V3 with static memory, and finally, doubling the performance one last time in V4 by fusing the control loop with scan. It's a fantastic visualization of the journey.
And what's the end result? A 24 times speed increase, going from 3.1 tokens per second in that initial naive version to 72.9 in the fully optimized one. This is what happens when you decide to cooperate with the compiler at every single level.
So what's the big takeaway for us as engineers? The huge wins didn't come from some new fancy algorithm. They came from a fundamental principle. You have to code for the compiler, not just for the Python interpreter.
The two decisions that mattered most were architectural. First, pre-allocating static arrays to kill that recompilation overhead. And second, using scan to fuse the control flow itself. The biggest wins came from optimizing how state and memory were managed, not the math inside.
You know, the developer who shared all this said they just hoped it would save someone else from having to stumble through the same painful steps. And that's what makes this so valuable. It's not just a result, it's a clear blueprint for any engineer who needs to make that trade, giving up some initial simplicity for ultimate performance.
Which leaves us with the big question that applies to any high-performance engineering project. When is it worth it? When do you make that trade? I mean, you just saw the numbers. A 24x faster generation is a powerful argument for taking on that complexity, but the learning curve and the fixed memory cost are very real. It's the core trade-off we all face when we're trying to deploy these massive models in the real world.